maybe some, well, let's see, yeah, we'll throw 16 in there. 16 would be an application of what we've been talking about. We still haven't fixed it. All right.
A quick question, real quick.
Okay.
For the MO theory, we're supposed to know during to second period or third period?
Second period.
Second
Only
period.
diatomics instead, right?
Second period diatomics, right?
So it would only be what? Oxygen?
Is it up to neon then?
Yeah, up to neon. Right. That's it for that, but you have to remember two different energy level diagrams. So let's review those energy level diagrams. When I think about molecular orbital theory, MO theory, what's the difference between MO theory and valence bond theory?
Molecule.
MO theory is more in-depth.
MO theory is more, it gives you more information.
Okay, MO theory is more in-depth, yes. More accurate, yes. What else?
We have to use, for the most part, we have to use computers for calculations, you know?
For calculations, you could do calculations with valence bond theory too. You know, both of you could do calculations with, but MO theory is more, you know, the difference is it's more, MO theory is the full quantum mechanical approach to molecules. Valence bond theory is
More practical.
the simplified approach. So what did I call it? I called the MO theory
The light version?
the light version versus the full version. The light version, how do you describe a bond? How's a bond described in the light version? Valence bond.
Either sigma bond or pi bond.
How do those bonds form?
Oh, they
Just
overlap
sharing the
Overlap of
versus of the molecular.
overlap of what?
Of the electron.
Of orbitals.
Of
Orbitals, atomic orbitals, right? Overlap of atomic. So in valence bond theory, though, you know, we talked about new atomic orbitals to accommodate the what? These new atomic orbitals. You learned about the SPDF orbitals, right? But we have new atomic orbitals to accommodate
More electrons?
not more electrons. Yeah, more electrons, but mainly you don't always have more electrons. And so it's not just more electrons. Sometimes you still have 8 electrons. 8 electrons before, 8 electrons after, an octet. It's to accommodate repulsions. This is what you guys should do, you know, when you review your notes is, you know, go through this and mentally, you know, or write it down, you know, this is to why, you know, these new orbitals are called, atomic orbitals are called hybrid orbitals. And so what you do is you put together the story yourself, you know, you build it up. And when you put together the story yourself, then it makes a lot more sense. Because if I say it, you know, how often does it register? You know, very little. You know, unless people just are into rote memorization. But if you put it into your own kind of interleaved story, then it's much better.
So it's to minimize repulsions between.
So yeah, this is my story. I'm just telling you my story. Like, you know, when I look at valence bond and MO, the book doesn't say this is the light version of quantum mechanics, this is the full version, but, you know, when I think about it, you know, that's the story that comes up. Well, this is the same thing you should do, is when you think about it, you know, you want it to make it memorable rather than, you know, because if nothing's coming up quickly, then, you know, it's not there yet. Yeah. I'm recording this. So we talk about MO. So MO, why, you know, if the light version's okay, or is the light version okay? Valence bond. Not all the time. So which one?
Fails for oxygen.
Yeah, it fails for oxygen.
Because it said that it's parametric.
Paramagnetic.
Paramagnetic.
Yeah.
Like
Oxygen is paramagnetic. Just saw a little video about that. Whereas valence bond theory predicts it's not paramagnetic. Predicts it's diamagnetic. Exactly. So that's good. And so it just shows that the electrons are distributed a little differently. And did you guys go through and look? I know that was difficult to look at, but if it's the same thing. It's the same thing that happens. If you generate a dot density diagram yourself, it's much more memorable than copying somebody else's down. Right? And so you want to generate yourself. The whole exercise yesterday is the only way you're going to understand that is to sit down with some colored pencils and just do it. It's not hard because you know what the orbitals are and what the orbitals look like. And then you just superimpose them on one on top of each other and see how the electron density is different, the electron cloud's different in MO versus, it's close though, you'll see it's similar in certain respects and it's different in other respects.
Do you expect us to draw for MO theory? Like, are we supposed to draw for MO?
Do I expect? Yes.
Only on the test.
On the test, if you look at my old exams, I've asked people to draw a pi 2p MO. Could you do that?
Oh, not the whole thing, but like the specific orbital?
Yeah, like a specific orbital. Is it possible that you could draw pi 2p? Not yet. Pi 2p is, you have a p orbital here and a p orbital here on the second atom. And then you just do this, right? What do you think constructive interference would look like? Doesn't that look like the pi bond we already just did?
Yeah.
But this is not a pi bond, this is a pi 2p orbital. That's it. If we do that, then we also have the anti-bonding. What does the anti-bonding look like? You see, when you do this, now the lobes repel each other, like that. This is the pi star 2p. The thing to do is, and this happens a lot, a lot of people can get overwhelmed with stuff and then they shut down or something. I've seen that happen. But if you just do this one orbital at a time, it's not hard. I think you've already done S, P, D. Right? So this is a few more.
Imagine drawing the second part.
Yeah, but how do they combine and become separate?
I get the first one, but
This is a linear combination. It's this. There's two ways. You flip this one over and then just do it, and you'll see that they're out of phase. This is why, if you look at the color coding, one's red, one's blue.
Wait, that should be because the plus minus will attract, right?
The plus minus do not attract. The plus and minus, do you guys remember what the plus and minus refer to? The amplitude. Do you guys remember when we square the wave function, what happens to the negative amplitude? Waves have positive amplitude and negative amplitude. What happens when we square it? It turns positive, so we color code it. So we don't lose the phase information, because phase information is very important because waves, if you try to add up waves like this is called destructive. The positive amplitude and negative amplitude cancel out. Have you heard of noise canceling? Headphones, right? They can cancel it out by, doing this. Destructive interference. That kind of stuff. But that's sound waves. Sound waves are different. Sound waves are pressure differences. This is light waves, and light waves behave the same in the canceling effect. Do sound waves move at the speed of light? No. Do sound waves move through a vacuum? No, sound waves will not move through a vacuum. Well, light will move through a vacuum. So what do you need? This is not the most important. Being able to draw an orbital like this is not going to be 10 points. Do you think so? No. What's going to be like 10 points? What's going to be like 10 points is being able to draw the molecular orbital diagram. The MO diagram, you don't have to draw the complete. You don't have to show the atomic orbitals doing what we call an LCAO. You know what LCAO is? LCAO is what I just did. LCAO is linear combination of atomic orbitals. Generates the molecular orbitals. LCAO generates the MOs, molecular orbitals. Molecular orbitals behave like atomic orbitals in the sense of 2 electrons maximum, Pauli exclusion, Hund's rule, off-bow principle, all those things hold. And so when we look at molecules, we have 2 charts. We have the Z greater than or equal to 8 chart. The Z greater than or equal to 8 looks like we expect. We kind of memorize this. You know, this is sigma 2s. This is for second period. For first period, so we're ignoring the sigma 1s, sigma star 1s, and we're just looking at the valence electrons. And so this is sigma 2s followed by the sigma star 2s. And where do these come from? These come from the LCAO of the 2s atomic orbitals. And so you could show the LCAO like this. The LCAO generates a sigma 2s when we constructive and a sigma star 2s when it's destructive, right, out of phase. Sometimes it helps to do the LCAO so you don't get the orders mixed up. Because what should come next? A sigma 2p or a pi 2p? Sigma 2p should be more stable, right? And so that's head on. You know, what I drew up here was a pi 2p. What's the difference in looking between a sigma 2p and a pi 2p? Here's a p orbital. Here's a p orbital. So what do you think? The positive parts are going to add, and the negative parts are going to shrink here. And so this is a sigma 2p. If we generate a sigma 2p, we also generate a sigma star 2p. So we flip this orbital this way, and so we'll have negative and positive. Negative and positive good? No. In electrostatic attractions, it's good. You know, but we aren't dealing with electrostatic. We're dealing with wave amplitude. And so here, in terms of wave amplitude, no, it's not good. So when we look at the nucleus, the p orbitals do this. In the middle, we call that a what? A node, right? And so this is the sigma star 2p here. Okay, the pi 2p's aren't going to be as stable because the electron density isn't within the internuclear axis. And so we got a pi 2p here and another pi 2p. What's the difference between the 2 pi 2p's? This is a pi 2p. The pi 2p. What's the difference?
X, Y, Y.
Yeah, right. One's in this plane, the other's in the perpendicular plane. Now we got the 2 cigar-shaped lobes. Okay, then we go to the pi stars. The pi star 2p and a pi star 2p. Again, these are just going to differ in the plane. You know? This. We good so far? Now, when we have a large Z, what does that mean? Someone write it down from yesterday. Or look at it from yesterday. What does a large Z mean? Tell me. A large Z means more, no, large Z means it pulls in the electrons closer. And which one should it pull in closer, the sigma 2p or the sigma 2s? The 2s are more penetrating. So when we look at the 2s, I'll label the 2s in green here. The 2s is like this. And the 2p are less penetrating. And so this is what's going to happen. When we have a large Z, this is not the scale here. Let's see if I can choose it. So, large Z means it's going to pull in the electrons tight, and it's going to pull in the 2s tighter than the 2p. And so when I look at the 2s are more penetrating, so look, you have to pull in tighter. This is the sigma 2s. And then the sigma 2p aren't as penetrating. And so the sigma 2p, so basically, the electrons can have their own kind of space. No, this should be more symmetric. The electrons have their own space. Dude. Yeah. Versus a small z. A small z isn't going to have the pull on electrons as a large z would. And so it doesn't hold any of them that tightly. And so when we get a small z, what happens is this.
Supposed to repeat it?
Yeah, it's not going to pull in as tightly.
It's supposed to repeat it?
Yeah, bigger. The bigger the z,
Smaller z. Smaller z. Always repeat it.
right, the bigger the z, the smaller.
Oh, okay.
The smaller the z, the bigger the orbital is. So the pull isn't as strong, the smaller z. And so what this does is we get repulsions. And so with a small z, we end up with repulsions. Repulsions because they kind of occupy the same space, same volume of space. And so what that does is it changes the this.
So when Z is greater than 8, then we start with
Yeah.
E.
Yeah. And so here, this is z is greater than or equal to 8. This is okay. But when z is less than 8, then this is what happens. If z becomes less than 8, then the sigma 2p and the sigma 2s interfere with each other. And it destabilizes the sigma 2s. Pops it up here. So this is z less than 8. We're going to get the sigma 2s. You know, the green orbital is the sigma, excuse me, not 2s, sigma 2p. Green orbital is the sigma 2s. The blue orbital is the sigma 2p, so the sigma 2p becomes destabilized here. See? Repulsion with the sigma 2s. Okay, does that make sense?
Why doesn't repulsion make the orbital flip? You know how you flip the order to P? Well, why is it?
Why does the repulsion make it? It doesn't flip, it just goes up in energy.
Yeah.
Why does it go up in energy? Because the electrons are. Here, if you have sigma 2p electrons, here, the 2s is, let's say the 2s is 2 electrons. You can throw an electron in the 2p. Do you see the 2p electron here have volume that doesn't interfere with the 2s, whereas here they're all in the same space. So you can get electron repulsion. Whereas this one keeps the 2s confined to a smaller volume. Does that make sense? And so because of the electron repulsion, electron repulsion, it bumps up the energy. And so the energy gets kicked out here. And so the net result of this is that you unfortunately have to learn 2 charts. What are the 2 charts that you have to learn? So this is for first period. Second period. These are the 2 charts you have to learn. Z greater than or equal to 8. Normal. So what is 8?
So that would be for oxygen.
Oxygen, fluorine, and neon. Z less than or equal to 7, or just Z less than 7. Do you see what happened to the PZ? I mean sigma 2p. Sigma 2p got bumped up. So this is the other pattern. It was down here, now it's up here. So we fill it differently.
In the test, do you draw the lines in between?
No, you don't have to. On the test, you just have to draw the middle part.
Well, that would be the dark lines in red, right?
This. This is what the middle part looks like.
How did it go from there to
Whoa.
Oh,
And rather than lines, they use boxes.
Yeah, wasn't it like you did it yesterday? Like you draw the middle lines? Like you draw
Look at just the middle line.
that and then the other one.
1, 1, 2, 1, 2, 1.
That's what I was.
Look at that.
So what's the box?
1, 1, 2, 1, 2, 1. It's the same. You see? It's the same except they use boxes.
And then you write those.
Okay, but that's for oxygen. It's going to be this. You're going to have these 2, 1, 1, and then it's going to follow this pattern, the 1, 2, 2, 1. Do you see the pattern, the symmetry there?
Oh yeah.
Look at. Do you see that pattern?
Oh yeah.
Do you see the symmetry in the pattern? And so you have these. This is 2 p orbitals follow this type.
When you fill the electrons
Mhm.
into the 2 boxes, do you fill those by adding? I'm confused with like filling up like the order.
Let's fill. Lithium has 1 electron, and we have 2 lithiums, so it's 2 valence electrons. And so you just fill it 1, 2. Then we say that this is diamagnetic because it's paired, and the bond order is 1 because it's 2 minus 0 divided by 2 is 1. So we have 2 electrons in the bonding region. In other words, the bond order is just how many net electrons. You know, every 2 electrons constitutes 1 bond. How many net electrons we have in the bonding region? Be2, well, beryllium has 2 valence electrons. B2 is predicted not to exist because the bond order is 0. The anti-bonding cancel out the bonding electron density. B2 is 6 electrons. B2 is the boron diatomic molecule. It's going to be paramagnetic. Bond order is 4 minus 2, 1. C2 molecule going on. It's going to be diamagnetic with bond order 2. So it's going to be a carbon-carbon double bond. And diatomic.
Why would it
You just take the bonding. 2, 4, 6 bonding minus anti-bonding 2. It gives us 4. 4 divided by 2 is 2. In other words, for every antibonding, you have to cancel out one bonding. So that leaves only 2 bonding pairs. Well, 2 bonding pairs is double bond.
How come BE doesn't have, it's not paramagnetic or diamagnetic?
Which one? BE2?
Yeah.
Because it doesn't exist. BE2 would be diamagnetic if it
Yeah.
existed, yeah. But since it doesn't, they just lost it. It doesn't exist because the bond order is different. N2 has how many antibonding? Has 1 antibonding. 1 antibonding will cancel out 1 bonding, which leaves us 3 bonding pairs. 3 bonding pairs would be a triple bond. We're going to have sigma electron density in the triple bond and high electron density. In fact, the electron density in the MOs of N2 looks very similar to the electron density in the valence bond. O2 is different though. O2 doesn't look so similar because of this paramagnetic here. What's the bond order? Well, we cancel out 1 antibonding, cancel out 1 bonding, so we have 1, 2, 3, and then we have these 2 antibonding, so we got net 2 pairs. And so the bond order is 2, double bonds. But, in MO theory, how is a bond described? In valence bond theory, this is the full description, this is what I was expecting. Overlap of atomic orbitals causes a greater electron cloud density in the internuclear region, which makes the bond. In MO, what makes the bond?
Combination of orbitals.
It's not the common. It's the what makes it. It is. That's all part of it. But the end result, what makes a bond in MO theory?
Is that the attraction of the...
It's not the making the orbitals. It's what we do with the orbitals. Because the orbitals could be there. We got lots of orbitals here, but we might not have any bond. In other words, here we made, the combination, it's called the linear combination of atomic orbitals. Yeah, we did that, but we still didn't get a bond. And so what makes the bond?
Having the electron.
What makes a bond is where the electrons are, is having more bonding electron density versus anti-bonding density. That's a bond in MO. That's what we're doing with bond order. When we do these calculations, 2 minus 0 divided by 2, that's looking at how much excess electron density you have in the bonding MOs compared to the anti-bonding MOs, and every 2 electrons makes a bond, so we divide it by 2. So that's the story behind that formula. But you want to understand the stories behind the formula to make them more meaningful. But if we look at fluorine, what's the bond order here? Okay, anti-bonding cancels out of bonding. These 2 anti-bonding cancel these 2. That leaves us with just 1 net bonding pair of electrons, which means it's a single bond. It's diamagnetic. Electron density, if you did electron density map of this, it's kind of similar to the electron density map of the UC. It would look different though, it definitely looks, actually it doesn't even look that similar. It looks actually quite a bit different. But from afar it looks similar. How about NE2? NE2, anti-bonding, cancels out all the bonding, which gives us bond order 0. And so these are the scenarios for diatomic. These are called homonuclear diatomics. Homonuclear diatomics means the same atom. What's heteronuclear diatomics? Yeah, different elements. In all cases, the sigma 1s and sigma 1s star molecular orbitals are filled but not shown. And so the 1s and the 1s star are shown because we're just dealing with the valence electrons here, rather than the total electron.
Question.
Yes.
If the bond order is negative number, what does it mean?
If the bond order is what?
Negative number?
No, it's never going to be a negative number. Impossible.
Impossible.
It
Or
will
it has
never
to
be
zero
negative.
or more.
Yeah.
That's right.
Yeah. Or because of how it fills, it can never be negative. It could be negative if you in an excited state, then the bond's for sure going to break. So, here, if you look at this, what is this? Diagram. Is this an energy level diagram? No. This is just a compact way of writing it. This diagram is how the homework is always going to be answered. Why? Because space. That's the only reason why. We don't have much space. So since a lot of people think this is the way that the homework's always answered, this is the way they should always answer it. No. They should always answer it like this, right? Or lines, use lines. You don't have to use boxes. Space. Special look at O2. O2 plus, is it going to be stronger bond or weaker bond? No, O2 plus. Stronger bond. Because O2 plus, you're going to knock out a antibonding electron. If you knock an antibonding electron out, it's going to be stronger bond. And so O2 plus is actually stronger.
How do you know that was a strong bond?
Because when you ionize oxygen, you're going to take an antibonding electron out.
Yeah.
And that's only going to help it, because the fewer antibonding, the better. And so if you recalculate, here it is. We take an antibonding electron out here, we recalculate it, the bond order comes to 2.5, which means it's stronger. Stronger bond. That doesn't mean it's stable, it just means the oxygens are held together more tightly. O2 plus is highly unstable because it's going to want an electron with charge neutrality. In valence bond theory, let's try this. In valence bond theory, pi bonds are always accompanied by a oh, you know what? I forgot.
Yeah, that was it.
Shoot. Oh, okay. Oh, you should. Don't worry.
That's my good.
Okay. I forgot.
You need to calculate every time.
Well, anyway, pi bonds are always accompanied by sigma bonds. Yes? Yes. Can the same also be said of an MO theory for diatomic? Are pi always accompanied by sigma? And the answer would be, well, let's see. We have pi here. Is there a sigma? Yes. So we always have sigma. Well, actually, no. Here, these cancel out. Whoa. These two cancel out, right? And so we just have pi bonding. And so no. And so these are the figures. What are these diagrams called? These diagrams are called MO diagrams. Molecular orbital diagram. They call it the molecular orbital occupancy diagram. We just call them the MO diagrams. Is this diagram an MO? In a way, yes. In a way, no. It's not a. This is a shorthand MO diagram. Okay, so we have oxygen. Continue on. Okay, what did we just do? We just did homonuclear. Now we're going to look at heteronuclear diatomic. And And so the first one we look at is carbon monoxide here. If we use carbon, what's carbon? Carbon Z is 6. Oxygen Z is 8. We have a conflict. Which chart do we use? The Z less than 8 or the Z greater than or equal to 8?
Greater than? Someone have a money?
Which one did we use? We use the Z. Is this the less than or the greater than?
Greater?
What is 3 sigma?
This is their labeling system. Don't worry about this. The naming of it. But look at the. Notice that the carbon monoxide molecular orbitals are ordered in the same manner as which one? The Z less than 8 or the Z greater than or equal to 8? Less than. So this comparison is a simple comparison. And so the sigma orbitals for CO are labeled 1 sigma, 2 sigma, 3 sigma, and 4 sigma because these orbitals are mixtures of 2s and 2p orbitals from both carbon and oxygen. So, you know, there's a great deal more mixing going along. You see? Look at this. There's more mixing of the orbitals going on. But we don't have to worry about it. We just look, okay, we use carbon's MO diagram instead of oxygen's MO diagram for carbon monoxide. And so for carbon monoxide, we look at it, and
But why is Z less than 8?
So we ignore the oxygen?
that's just what's observed. Another thing is, look at this. Which one's more electronegative, carbon or oxygen? Oxygen. Oxygen has a greater Z effective, so look at the difference in 2s. Oxygen 2s is a lot smaller than carbon's and lower in energy. Something. So this got pulled down. All right, carbon monoxide, how many electrons? 4 valence electrons for carbon, 6 valence electrons for oxygen, 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Carbon monoxide, diamagnetic or paramagnetic? Diamagnetic. What's the bond order? Bond order. So bonding, anti-bonding, cancel.
So, it's 3. 3.
3?
I got 3.
Is that wrong?
Where's the antibody showing? It's the 2 sigma.
2 sigma.
Wait, isn't it?
It should, sorry.
Oh, actually, no, that's the 3, this one. The 3 sigma. This is the antibody.
How do you know that?
Are they both? It doesn't show star there. Are they both antibody?
No, they're not. Because we know one is bonding, the other is antibonding. And actually, the order it typically goes is this. But there's too much mixing going on here, so it's confusing. And so this is, just look at, have you memorized the pattern? Look at it. Bonding, antibonding, bonding, bonding, bonding. You see, we're using the red. So this is the pattern. Bonding, bonding. Oh, bonding, antibonding, bonding, bonding, bonding.
So it's
3. Bond order is 3, which would be a triple bond. Okay. What if we do this? If we knock an electron off carbon monoxide, does the bond get weaker or stronger, or stay the same?
Knock an electron.
Yeah, knock an electron off carbon monoxide, the bond gets weaker.
It becomes by
Let's look at cyanide. If we look at cyanide, which diagram should we look at for cyanide? Yeah. So let me get the diagram here.
So is it a general rule if it's a Z less than 8, and Z greater than 8, bonding, use the Z less than 8 diagram?
Well, okay, if you can use carbon monoxide as the example, yes, then that would be yes. But you'd have to look at more diagrams to see, how things mix to do it. And so for carbon monoxide, yeah. For other things, sometimes it's the higher Z that will dominate. Okay. Look, this will be another heteronuclear one. Cyanide is a lot easier because both carbon and nitrogen are less than 8. And so we're going to use this one here. And so carbon has 4, nitrogen has 5, and the negative charge adds 1. And so cyanide is going to have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so what is the bond order here? Well, these cancel, that leaves us 3 pairs. The bond order is 3. It's diamagnetic. The cyanide, 3 diamagnetics. In fact, cyanide looks just like this. You have carbon and a nitrogen. We'll put the nitrogen in negative so it has an extra electron, and then Cn minus 10 electrons. This is exactly what it looks like. So that's MO. Now, so far we just focused on MO for diatomics. Why only diatomics? Why only diatomics?
Triatomics and more will be a lot more.
Yeah, a lot more complicated. So we aren't going to worry about generating MOs for triatomics or anything more complicated. But we will look at some more complicated molecules, like benzene. If we look at benzene, what does valence bond theory tell us about benzene? What's the hybridization on the sp2? These are all sp2. This is one resonance form. This is another resonance form. There are 2 resonance forms we can draw for benzene. These are them. And for sp2 hybridization, we have what type of geometry of sp2 orbitals? Trigonal planar. And then what's happening with the p orbital? The p orbital. Where's the p orbital here? Can you see it? It's sticking out, right, of the board. Yes? No?
Yes.
I'll draw it out. Okay, so we'll spend a little bit of time talking about benzene. I'm going to draw, not like that, I'm going to draw semi-in kind of perspective here. I'm going to tilt this benzene ring on its side, and then we'll try to look at the p orbitals in profile. You got it?
Yeah.
Okay, when we look at this structure here, I have a double bond here. And so this one is going to be a double bond. This one's a double bond. And this one's a double bond. And so I have 3 double bonds. Do you see the pp pi bond? Yeah. If I look at the other resonance forms, what did I do? I just switched it from these p's to these. And so I just move it. The pi bonds. But we know that neither of these resonance forms are correct. What's correct? It's the hybrid. And so the resonance hybrid just says, if I can put the electrons here or here, then they're capable of moving, right? And so all I'm going to do is I'm just going to spread them out over the entire. And so now all the bonds are equivalent. They're all 1.5 bonds. And so this would be the resonance hybrid. All the bonds are the same, bond length, bond strength. In fact, you know what? This should be stronger than a single bond, weaker than a double bond, right?
Yeah.
But you know, in benzene, the bonds turn out to be unusually strong.
So it's stronger than the double bond?
Well, not stronger than double, but unusually strong and stronger than what they're expected to be, right? Not stronger than a double bond. And the reason is because of this. It's called resonance delocalization of the electron density, how it's spread out. This causes this to become more stable. Resonance delocalization. And so the more you can spread out the electron density, this is delocalized pi bonds, the more you can spread out the electron density, the more stable the overall structure becomes. And so there's a simple rule for this. The simple rule is the more resonant structures you generate, the more the electron density can spread out and the more stable. And so one way of getting a gauge on something is how many resonance structures can you draw out? The more the better. For stabilizing things. Okay, so here what we can see is we can see the, what are we looking at in the purple? You tell me. We're looking at the sp2 orbitals and the sp2 sigma bond. So this is called the sigma bonding framework or network. Over here we're looking at the p orbitals and the pi bonding. And so we connect these, or we just delocalize all the pi electrons over all the orbitals. And so this is what we get. Do you see this ring here represents this delocalization of the pi bonding electrons over all the atoms. And so this is the symbol for the benzene ring. Benzene ring has this added stability of the resonance delocalization of electrons. Oops, I forgot to put the camera over there. You just look in that book. Oops. Well, here it is. This is called what theory? This is valence bond theory, right? Valence bond theory. In molecular orbital theory, we don't have localized, these are called, like, for example, if I just connect just these two orbitals, this would be called a localized pi bond here. Right? And the only reason I delocalized, the only reason I delocalize this is to do the hybrid. So here's my localized pi bond, but I'm going to delocalize it over all p, right? In MO theory, all the molecular orbitals span the entire molecule. And so MOs are naturally delocalized electrons. And so in MO, how does MO theory handle benzene? Well, let's just take a look at how MO theory handles benzene. These are the MOs that are generated from benzene here. This is a pi MO. What does this pi MO look like? This is it. And when we look at the pi MO, if we have electrons there, are the electrons localized in one bond? No, they're delocalized over the entire molecule. And then we have these other, these are more localized here in this one. But when you look at this one, it's localized. And so these are the molecular orbitals. And we're going to have you draw these ones out. Are you going to memorize these ones? No. All right, it's too much. Don't you think? This is way too much. And so when we look at the MO theory for benzene, we get essentially the resonance hybrid of valence bond theory, right? This is it here. The molecular orbital representation of the pi bonding of benzene. This is the computed pi molecular orbitals of benzene. Do you see that? it looks like the hybrid. And so, forming this resonance hybrid in valence bond was an after the fact kind of thing. But here in MOs it works. And so this is just another example of this. In valence bond theory, what is the hybridization here? sp2, sp2, sp3. And so we have these two. And then we would come up with the resonance hybrid. The resonance hybrid. But how does the resonance hybrid work? Because this is sp3, this is sp3, you know? It doesn't quite look like benzene. Benzene was very nice to us. Benzene was very nice to us. Why? Because all the p orbitals were nicely aligned. Like this. You see how all the p orbitals are nicely aligned here? But if we look at ozone, it doesn't look the same. And so let's do, why don't you, actually, do we have time? Why don't I do ozone on the board? If I do ozone on the board, I'm going to do oxygen. What is it? sp2. Oxygen, sp2. Oxygen, sp3. So this oxygen, the sp3 oxygen is going to have how many lone pairs?
2.
This one.
3.
3 lone pairs. And then we got this going on. This oxygen has 1 lone pair here. This one has 2 lone pairs. And then, you know, there is a pp pi bond. Where is it? Sticking out. There's a p orbital sticking out here, and a p orbital sticking out here. Like this. Right? In order to switch from this resonance form to this resonance form, what has to happen to the hybridization here? This is going to convert to sp2 hybridization. This is going to convert to sp3 hybridization. We can just show the arrows moving here. To show the arrows moving, we take a lone pair, bring it to the bond here, pop these out here. Right? That's fine. And so what we'll do is bring a lone pair, bring it into the bond, convert this to sp2, and then pop these out, pi electrons out here. Right? Now, the situation comes up with the resonance hybrid. Now, what's the hybrid going to look like for ozone? Now, the hybrid's going to look like this. The hybrid is going to look like this.
What about the lone?
Yeah, now, what is the hybridization on the oxygens now? Because what we have now is we have that one extra lone pair shared between the 2 oxygens here. You see it? And so I show the one extra lone pair being shared between the 2 oxygens with the dash. And so what is the hybridization here? Okay, so this is this is what we can do here. And what we can do to generate the hybrid is then what we're going to do is normally this should be sp3, right? But what we can do is we're going to instead hybridize it sp2. Right. If we hybridize it sp2, it doesn't seem as stable because of the repulsions here. Because what's going to happen with that extra lone pair? The extra lone pair now is going to go into the p orbital.
The lone pair?
Yes. It has 3 lone pairs, right? so this extra lone pair now goes into P. Well, there's greater repulsions, right? There's greater repulsions, but this can do it because now, if I look at all the P orbitals,
They all have 5 bonds. Wait, no, they all have,
all the P orbitals are going to be lined up like
they all have multiple.
this. And what we can do is then now we can delocalize electron density in this p orbital network. Does that make sense?
Why does it go to the P orbital?
And so normally you wouldn't do this. You wouldn't hybridize this sp2. It should be sp3 to minimize the repulsions. But the reason it's going sp2 is because now you can delocalize one lone pair into the pi bonding network, or the p orbital network, which helps stabilize things. In other words, spreads the electron density over more of the molecule. Does that make sense? This is valence bond theory. Well, for MO theory, you don't have to do this, because in MO theory, what do we have? You know, in MO theory, we got a MO that looks like this, and it's just normally going to delocalize the electron density over the entire molecule. And so when we look at this, the delocalized pi molecular orbital, structure of the ozone, okay, here's a sigma. The pi molecular orbitals are assignments of electrons to them are discussed in points 3 and 4. So let's go to points 3 and 4. But anyway, here we go. With VSEPR, we predict trigonal planar electron group geometry. The hybridization scheme chosen for the central oxygen is sp2. And although we normally do not need to invoke hybridization for the terminal atoms, this case is simplified if we assume sp2 hybridization for the terminal oxygens as well. And so they're going to make this sp2 and this one sp2. Why are they making this one sp2? It should be sp3. Okay, we assume sp2 hybridization for the terminal oxygens as well, thus each oxygen atom uses the orbital set sp2 plus p. The three unhybridized 2p orbitals combine to form the three molecular orbitals. Okay, this is going into molecular orbital, but we can also think of the three unhybridized 2p orbitals as forming a delocalized electron network in valence bond theory. This is valence bond. Now we're clicking to MO theory. In MO theory, we generate our MOs by doing an LCAO of the atomic orbitals. So here, we use these sp2 hybrid orbitals to make new sigma, and we use these p's to make the new pi's. So here we have one new MO, another new MO, another new MO. Normally we have a bonding and an anti-bonding. But when you take three orbitals, an odd number of orbitals, when you have an odd number of orbitals, we're going to form bonding. For every bonding, we form an anti-bonding. That leaves one orbital left over. And that one orbital left over is called a non-bonding orbital. So we generate a bonding, an anti-bonding, and a non-bonding. But in other words, the MO is going to show this as being naturally delocalized. You know? And so the MO is going to be more accurate. Okay, what do we do here? Normally what we do here is we call this one, what oxygen is sp2, nitrogen is sp2, this oxygen is sp3, this oxygen is sp3. Normally we have these, you know, the three resonance forms. Then we generate the hybrid. The hybrid's not shown here, but in the hybrid, what do you think we're going to hybridize them as? Because what we're going to do is we're going to delocalize the pi electrons over the entire molecule. In order to do that, we need, in valence bond theory, we need p orbitals, right? And so we're going to rehybridize everything as sp2. So here they show rehybridize it as sp2 and then put the extra electrons in the overlapping p bonding. So we've got p orbital here sticking out, p orbital here sticking out, p orbital here sticking out, p orbital here sticking out. See that? This is what it's going to look like. This is what it looks like in, in valence bond and MO. In valence bond, we hybridize everything sp2 and then just kind of spread all the electrons out. In MO, we naturally get it. This is one of the molecular orbitals in MO theory. And so MO theory, we don't have to do all this other stuff. It automatically comes out this way. In valence bond, we have to modify the resonance structure to make it come out like this. So these are the atomic orbitals that we're combining. They don't show us the molecular orbitals. This is what happens in this. Do you see this? This one we don't have to do any kind of weird hybridization because what is this? sp2? All these are sp2. Where are the p orbitals? They're all sticking up. They're all lined up. So that means we could delocalize the pi electrons over all these p orbitals. Okay, this here is called an aromatic hydrocarbon. And it's because it has this alternating double bond. Alternating double bonds like this means we're going to get that extra stability from delocalization over the entire structure. This is the same thing. Okay, but you see all the pi electrons can delocalize over here, but you see these are localized. Can we delocalize these out? No, because this one is sp3 actually, this carbon. Each kink represents a carbon. And so there's a carbon there. The hydrogens aren't shown for clarity. All right, now let's talk about this. This is with 2. If we take 2, we get 2 MOs. If we take 3, we get 3 MOs. A bonding, a non-bonding, and a anti-bonding. We take 4, we get 2 bonding, and we get 2 anti-bonding. We take 5, we get 2 bonding, 2 anti-bonding, and 1 non-bonding. If we take an infinite number, let's say we take an Avogadro's numbers worth, we're going to get an Avogadro's numbers worth of MOs. And the MOs are going to get so, this is only 16, but the MOs are going to get so tightly spaced that we start calling them bands of MOs. Bands of MOs. And so this is what happens for metals. Metals, we have the electron C model, like this, where the electrons are pretty well delocalized over the entire metal. Or we look at something called band theory. Band theory is bands of MOs. So if we have an Avogadro's numbers worth of lithiums, we're going to have an Avogadro's numbers worth of molecular orbitals, and these form energy bands. Normally, this is what we see. Normally we see, the filled MOs here, the bonding, and then empty anti-bonding here. There's usually an energy gap. And in an insulator, we'll have a pretty big gap here. The gap is UV or X-ray to pop up an electron up here. So insulators, the semiconductor is visible light. Visible light hits this and pops an electron up here. When an electron gets popped up into an empty band, how big is the MO? MO spans the entire crystal of metal. And so if an electron pops up here, it's free to move. It's totally delocalized and free to move, right? And so we can get these to conduct electricity by shining light here. If we shine light here, pops electrons in what we call the conduction band, and we get electrical conductivity. For metals, there's an overlap here between the anti-bonding and the bonding MOs. So all it takes is thermal energy. A little bit of thermal energy conducts electrons. here. The electrons are free to move. Yeah. Or it's a half-filled band of MOs. If we have a half-filled band, then there's empty MOs here. That's electrons can move freely. And so this is a brief introduction to band theory, which is talked more about in Chem 1B. So I'm not really going to talk about this, about doped semiconductors. We're going to skip that. And then we're going to look at an application. So let's try to put some of this stuff together in an application here for acids and bases. Arrhenius acids are just H plus AQ, anything that gives H plus AQ. Arrhenius bases are anything that gives OH minus. And so we're going to look at acids and bases. And so in the syllabus, we cover 16.1. 16.1 isn't even one page. And then we cover 16.2. Bronsted. What is a Bronsted acid? Proton donor. What's a Bronsted base? Proton acceptor. And so we cover 16.2. Proton donor, proton acceptor. This case stuff, we don't cover. And so that's less than a page also. So this case stuff, skip it. And then we hop over to 16.8. 16.8. We skip all the calculations. And now we're looking at molecular structure and acid-base behavior. We look at the strengths of acids based on structure. Strengths of acids based on structure. That's 16.8. So 16.8 is the most important. 16.9 talks about acids and bases. Sorry. 16.9 talks about Lewis acids and bases. Do you remember what a Lewis acid is?
No.
Electron pair acceptor. A Lewis base? Electron pair donor. Do you remember the example I did with carbon dioxide and water? Yes? Or it doesn't even register, so long ago. It was a long time ago I talked about CO2 and water, Lewis acid base. All right, so basically we're going to spend most of our time on 16.8, molecular structure and acid-base strength. And so let's talk about that now. Let me use the board.
11.
Electron pair.
Yeah, it's number 16. All right, let's start. It's not a lot because, you know, valence bond theory, you're going to have, right? Some MO theory. So we spent all our time talking about Lewis structures, shapes, valence bond theory, MO theory, right? 16 is just an application of that. And so let's look at it. We're going to look at strength of acid first. So 16, if 16 were different material, then yeah, you know, it's just more stuff. But 16's the same stuff. The strength of acids. Well, actually, let's let me back up just quickly. 1 second.
Oh, I'm sorry, no, I was just stretching.
Okay. Let's look at applications. Applications for chapter. Sorry, let me erase this. Okay, one application is estimating delta H. Delta H is about equal to the sum of the bond energies for the reactants minus the sum of the bond energies for the products. This is the bond energies. The bond energies, this is in chapter Chapter 10. There's a table. You know, the average bond energy. The average bond energy for a hydrogen-oxygen bond was 466 kilojoules per mole. Remember that? But to break a hydrogen-oxygen bond in water costs 500 kilojoules. So this is just an estimate. This is an estimate because we're just using the average. And so all this says is if we have stronger bonds in the product is going to make this exothermic. Stronger bonds in the reactant is going to make it endothermic. That's all. We want to go from less stable to more stable. That's favorable.
So that's the application, that's chapter 16.
No, actually, this application is chapter 10.
What?
Okay, the next application we're going to do is the strength of acids and bases. The strength of acids and bases is chapter 16. So let's see if we can apply some of the stuff that we learned here. Okay, what makes a strong acid? What makes a strong... We're going to go with Bronsted acid. Bronsted acid. It completely ionizes in water. In other words, the hydrogen ion breaks off easily, completely. Right? And so what we want is, we want a weak HB bond. HB bond. This is most important because we need to break the H off easily. So we have HB goes to H plus B minus, right? B is just the conjugate base. And so the weaker this bond, the stronger the acid. And so this is important. 2, we want a greater positive charge on the hydrogen. And so the more polar the HB bond is, the better. The more acidic. And so here, if we look at HB, the bigger the delta plus on H, the better. Because the bases, like hydroxide, are going to be attracted to the positive charge. And so this should be more acidic than this, right? Three, the stability of the conjugate base of B minus. The more stable B minus is, the stronger the acid. We look at two things in the stability of the conjugate base. Basically, we look for charge delocalization. Charge delocalization, we might look at, induction, or we might look at resonance delocalization. Resonance delocalization this is more minor, this is more major.
What do you mean by more minor, more major?
Resonance delocalization delocalizes the charge much more effectively than induction does. Induction is if you have something sucking away electron density, like an electronegative atom, sucking away electron density. All right, so let's look at some acids and then compare. So the first example we'll look at is HCl, HBr, HI. HCl, HBr, HI. HF. Sorry, let's throw in HF. Which one do you expect to be the strongest acid? Hydrofluoric? The strongest acid is HI. This is the strongest. This is the weakest. The strongest is the weakest.
Is hydrofluoric the weakest because the bond is very strong?
The bond is strong. A couple of reasons. I'll talk about it right now. Hydroiodic acid is the strongest because we got it, you know, when we look at HI, what is the, look at it this way. What is, we call it sp3, right? But it's got huge orbitals. In fact, we might not need to hybridize iodine because the orbitals are so big, the repulsions. Why do we hybridize? To minimize the repulsions, but the repulsions probably aren't so big, right? Probably don't need to hybridize, but you know, to keep it simple, we're going to hybridize everything. And so this is sp3, and this is going to bond to a s orbital on a hydrogen. Okay? And then we look at the electron cloud here. Now, there's one electron here, one electron here. Versus HF. It's sp3. Show the sp3 set. Which one's going to have a stronger bond? HF for sure is going to have a stronger bond.
So why would it be that's why it's very hard to
If you're a base, like a hydroxide. A base like hydroxide comes along and tries to pull the hydrogen off. Which hydrogen will be easier to pull off? The HI. This hydrogen will be easier to pull off. Why? Because the bond is weak.
So does bond strength have more significance than polarity?
Yes. Bond strength is, that's a good point. Bond strength, in terms of bond strength, we predict HI to be the strongest acid and the weakest bond. In terms of polarity, hydrofluoric should be, because HI is going to have a very small delta plus, HF is going to have a very large delta plus. So in terms, you know, hydroxide, which hydrogen is it more attracted to? Which hydrogen is it more attracted to? Hydroxide. HF. Hydroxide is more attracted to this hydrogen, but it can't pull it off.
Is it because it's in higher polarity? It's
Yes.
Okay.
It's more attracted to this hydrogen, but it's going to have a hard time pulling the, actually it's easy time because hydroxide can easily do that. Let's do something weak. Water has a harder time. Water doesn't have a full minus charge, it has a partial minus charge. So water is going to have a hard time pulling the hydrogen off HF, whereas pulling the hydrogen, it's less attracted to this, but that's easy to pull off. And so this water can easily strip out. Much harder time here. Hydroxide's powerful enough it could do both easily. Actually. So hydroxide was the wrong one to pick. Okay, does that make sense?
Yeah.
And so this is why bond strength is the most important factor. And so if we go back, and I'm going to take a look at the numbers here. So let's look at the numbers here. The numbers will, the bigger the number, the more acidic it is. bigger the number, the more acidic it is. HI, 10 to the 9th, big number, right? Very acidic. HF, 10 to the minus 4. Look at HI 10 to the 9th, HBr 10 to the 8th, HCl 10 to the 6th million. And then HF 10 to the minus 4. HF is a little weird, isn't it? Does HF have, this would be a million, billion, 10 billion. Is HF's bond 10 billion times stronger than HCl's bond? Is that right? No. There's something else going on with HF. And there's something else that's going on with HF is called ion pairing. HF is unusually weak. It's unusually weak because of this. The hydrogen doesn't completely break off. And so what happens is we get an H plus and an F minus, and they're stuck together. You know, it's partially broken. And so it needs another hit to break it off, because these ions are strongly attracted. And finally another hit comes along, and then it could separate the ions.
Okay, so what you're saying is
So when you knock off a proton off HF, boom, the proton sticks around the fluoride. It doesn't leave. You know, when you knock out proton off HCl, it can leave. You know, the interaction goes quite a bit weaker. But HF, because of the small size of fluoride, has a strong electrical attraction, so it doesn't want to let it leave completely.
So it's still.
It hangs on. It hangs on.
and like
It hangs on. Whereas HCl doesn't hang on. HCl, when you break that bond, the interaction is weak enough that they can go their separate ways. You know,
so in order to break it off completely,
it takes a second hit,
okay.
a bit of energy.
Okay.
And so it needs something else, something along to come along and break it apart. And so it's kind of stuck together. Does that make sense?
Yeah.
And so HF is unusually weak. These guys are strong bonds. The hydrogen-carbon bond's strong. You know? But look at the 10 to the minus 60. But you know, I told you, is there only one factor? No, in these numbers there are multiple factors, and they all work together. And so we're going to start looking at these multiple factors, but we're out of time. So we're only looking at one factor today, and that is bond strength. So not all of chapter 16 will be on.
So you're probably like the other half on the final.
Yeah. Yeah, test is on Thursday. Test is on Thursday, so I'm sure you're going to enjoy your Thanksgiving holiday. No, not really. Oh no. Yeah. Yeah, just this, the HF, HCl, HBr, HI. That's all.
40? What happened? It's time to switch to the calculator.
No, it's the same.
Yeah.
When it's